Welcome all. Today I am going to present about new method to perform data reconciliation with OpenModelica and ThermoSysPro. This is a joint work done with EDF France, RISE and Linköping University Sweden. What is data reconciliation? The main purpose of data reconciliation is to improve the accuracy in measurements by reducing effects of random error in data. The current underlying problem is how do we reduce measurements uncertainties on energy systems, for example, power plants, power grids, etc., as the system constantly evolves in time. Data reconciliation solves the above problem by using a static model of the system in order to correct the measurements such that they fulfill the model's equation. The measurements are thus reconciled and the reconciled uncertainties are lower. Data reconciliation is a VDA 2048 standard. The benefit we get from data reconciliation is regain satisfactory operational margins from the reconciled measured values thanks to better estimate of the plant state. How does data reconciliation work? The data reconciliation is well expressed by the following mathematical notation. X cap equal to set of x cap I, where I greater than or equal to 1 but less than n are measurements with uncertainties given by the correlation matrix Sx cap as defined here. C of x bar equal to 0 is a set of equations that constrains the measurements. We basically call this set of equations as auxiliary condition equations through which the variables to be reconciled are computed. They are assumed to represent the perfect physical behavior of the system. The equations that fall of this assumption must be removed. Obviously, C of x cap not equal to 0. But the reconciled values satisfy the auxiliary condition C of x double bar equal to 0. The larger the C, the larger the uncertainty reduction. And hence, the reconciled values can be obtained by solving a constraint optimization problem represented by a Lagrange multiplier method. J of x bar equal to minimum of x minus x cap multiplied by inverse of the correlation matrix multiplied by x minus x cap with C of x double bar equal to 0. Here x is basically the initial measurement values given by the users, and Sx, the correlation matrix, is also given by the user in the form of an input CSV file. How to perform data reconciliation with the Modelica model and OpenModelica? In order for a Modelica model to be eligible for data reconciliation, a Modelica model should contain only exact physical laws. It is up to the user to decide whether the physical laws used are exact. However, most of the Modelica model contain boundary conditions that represent assumption on how the environment influences the system. These boundary conditions must be removed, and we must have a set of auxiliary condition equations which computes the variables to be reconciled. Here the boundary conditions are usually the constants and parameters. The main difficulty is how do we do this automatically by removing the boundary conditions and just extract only the auxiliary condition equations which can compute the variables to be reconciled. The solution we proposed is we developed an extraction algorithm within the scope of this work. But the challenging part is the extraction algorithm is not quite easy. We did so many iterations, and then we finally developed an algorithm which can work on both small and larger examples. How do we define the data reconciliation problem in OpenModelica? Is basically by tagging the variables of interest and boundary conditions. Consider the small example presented here, pipe 1, which has three variables and 3 equations. Here the variables to be reconciled are q1 and then q2, and they are tagged using the uncertain keyword, uncertain equal to uncertainty.refine, and the boundary conditions are tagged using the annotation OpenModelica boundary conditions equal to true. Once we tagged the variables to be reconciled and the boundary conditions, we can use the extraction algorithm which extracts the auxiliary conditions equations so that variables q1 and q2 can be reconciled. How does the extraction algorithm work? The initial Modelica model, after tagging the variables of interest and boundary conditions, we compute the BLT of the Modelica model, and then we remove the binding equations from the BLT. The binding equations here are usually the constants or the parameters. Once we remove the binding equations, we extract the set of equations from the BLT, which computes the variables of interest. We call that set of equations as EBLT blocks, which is represented as EI. And then for each equation in the EI that computes the variables of interest xi as given by the BLT, we extract a set Si of intermediate equation that compute the intermediate variables involved in EI. If Si contains an equation that involves a boundary condition, we must remove the boundary condition and replace the boundary condition equation in the Modelica model by the variables of interest xi equal to 0. Continue this procedure until all the boundary conditions are eliminated, and then we extract basically two sets of equations. Set C, which is basically the auxiliary condition equations that computes the variables to be reconciled, and set S contains the set of intermediate equations which computes the intermediate variables in set C. Removing one boundary condition which influences the variables to be reconciled decrease the size of set C by 1 unit, and therefore the uncertainty reduction. Experimenting the extraction algorithm on a simple example, splitter Modelica model. In figure 2, you see the ThermoSysPro model of splitter in OpenModelica. The model basically contains one pressure source, 3 pipes, 2 mass flow rate sink, one volume, and a thermal power plant. And in figure 1 of the splitter, you can see that there are 9 variables to be reconciled, namely Q1, P1, T1, Q2, P2, T2, Q3, P3, and T3. And we also have the boundary conditions to be eliminated, namely P1, H1, P2, H2, and P3, H3. These boundary conditions need to be eliminated if they influence the variables to be reconciled. The objective of the extraction algorithm is to extract the fundamental equations, namely one mass balance equation, one energy balance equation, and 3 momentum balance equations from pressure losses to the auxiliary conditions equations, that is set C, to have the best uncertainty reduction. In this slide, we present some of the results from the extraction algorithm applied on the splitter model. The boundary conditions are represented as Bj, and the variables to be reconciled are represented by xi, and xi equal to 0 represents the variables of interest detected at the boundary conditions and replaced by the variables of interest xi equal to 0. Let's take the first row P01 and the variables to be reconciled are P3, P2, and P1. We start with P3. And we see that we detected the boundary condition equation P01. We remove that boundary condition equation P01 and replace the variable of interest P3 equal to 0. And at row 2, we see we start with Q2 and we detected boundary condition equation Q02, and we remove the boundary condition equation and replace Q2 equal to 0. Similarly, we do it for the variable Q3 and T equal to 0. And then we finally extract set C, which is basically set of all the equations which compute the variables of interest minus set of all equations that are replaced by xi equal to 0. In this case, you see that we have eliminated 4 boundary conditions equation P01, Q02, Q03, H01, and then we also eliminated some of the auxiliary condition equations such as P3 equal to 0, Q2 equal to 0, Q3 equal to 0, and T is equal to 0. And then we finally have 6 equations in set C which can compute all the variables of interest Q1, P1, T1, Q2, P2, T2, and Q3, P3, and T3. And at the end of the algorithm, you can see that we are still left with 2 boundary conditions equations H02 and H03, but they do not influence the calculation of variables to be reconciled. In this slide, we present the numerical results from the data reconciliation algorithm on the splitter model. In the left hand side, you see a table with 3 columns, variables, which is basically the variables to be reconciled. and the measured value, which is the initial measured values provided by the user, and then weight, which is basically the half width confidence interval, which is used to create the covariance matrix Sx. These values are provided as inputs by the user in a CSV file, and then in the right hand side you see the data reconciliation results with the reconciled values and the reconciled weight and the individual test. And you can see the reconciled values are very close to the initial measured values, and the individual test shows that the reconciled values and the measured values are correct. And the below table presents another configuration of a splitter model where we reconcile only the mass flow rates Q1, Q2 and Q3. In this slide, we will see how to run data reconciliation in OpenModelica. After loading the Modelica model, in this example 5.1, we have to define the data reconciliation problem by tagging the variables to be reconciled, namely Q1 and Q2, and the boundary conditions P. After defining the data reconciliation problem, now we are ready to run the data reconciliation procedure, and this can be done by choosing the simulation setup window in OpenModelica, and then you can choose the tab data reconciliation and select the algorithm data reconciliation, and then select the measurement input file, which is a CSV file which has 3 columns, namely the variables to be reconciled and the initial measured values and the weight. These must be provided by the user, and the third and fourth argument, correlation matrix input file and epsilon, are optional. Once we have given these values, we can press OK. After the data reconciliation procedure is completed, a nice HTML report is generated with useful information to the user. The overview section contains information about model file, model name, directory, the measurement input file, correlation matrix input file, and the generated date and time of the HTML report and by which OpenModelica version. The analysis section presents users with information about number of auxiliary conditions, number of variables to be reconciled, number of iterations to converge, and etc. The auxiliary condition presents users with the auxiliary condition equations extracted from the extraction algorithm, and the intermediate equation presents the users with set test equations extracted from the extraction algorithm, and the result section presents the users with the reconciled values and the reconciled half-width confidence intervals. To conclude the work, to perform data reconciliation on a Modelica model, we need to automatically extract the auxiliary condition. To do that, we developed a new extraction algorithm and implemented in OpenModelica. The extraction algorithm has been validated on small examples built with Modelica library ThermoSysPro. The extraction algorithm has also been successfully tested on larger examples that represent the secondary side of a nuclear power plant. The larger model contains 2002 equations and variables. In that, we chose 26 variables to be reconciled, and the extraction algorithm extracted 23 auxiliary conditions. And finally, this work democratizes the use of data reconciliation, so no need for redeveloping the models in the dedicated software. Future work: have the new method certified by VDI 2048 body, compute the values of the boundary conditions from the reconciled values. Here the boundary conditions represents the eliminated equations from the extraction algorithm. We need to use those equations and compute the values of those boundary condition variables from the reconciled values. And then finally, solve numerical issues apparently linked with the use of the IAPWS IF97 for the properties of water and steam. Thank you.